Hi everyone, my name is Menglong. I'm a PhD candidate in mechanical engineering in Villanova University. The topic of my presentation is numerical simulations, odor plumes in insects. First, let me ask a question. What is odor plume? The first thing comes to my mind is smoke, its odorant, and its filamentous. So odor plume is just a bunch of dynamically evolving odorant particles, right? Yes, mostly. But the odorant particles we are talking about can be very small, like water molecules. At this small size, these odorant particles diffuse into their ambient. We use the term diffusivity to describe the extent of this phenomenon. Now imagine a puff of smoke in front of you. How do you move it? Yes, you blow. The transport of odor plumes is determined by the background velocity field and the aforementioned diffusivity. But how do we numerically simulate the transport of odor plumes? A series of equations, continuity, momentum, and odor advection diffusion equations were developed to describe the fluids. And all we need is to provide the initial conditions and the conditions on the boundaries. In our simulations, the first step is to quantify the background velocity field by solving the continuity equation and the momentum equation. The second step is to solve the odor advection diffusion equation to obtain the odor field. It sounds simple, but what we did have never been done before. Enough for the talking, let's see some results. The videos from left to right are odor plume side view, odor plume top view, streak line side view, and streak lines top view, respectively. Streak lines are basically the movement of points that are raised in the upstream fluid. Now let's decrease and increase the diffusion of odor plumes. As diffusion increases, odor plume tends to diffuse more to its ambient. Pretty straightforward, right? With strong diffusion, the odor concentration on the antenna decreases. Now let's change the flight velocity. When the velocity is low, the odor plume is pushed above the insect head. We see that the odor plume cannot be perceived by the insect. But the flapping wings in this case are able to induce odor plume from other locations, thus greatly increase the sampling range. As flight velocity increases, the odor concentration on the antenna increases, but the sampling range decreases. This can explain the two behaviors in odor-guided flight, that insects zigzag at a low velocity when trying to find the odor plume, and surge upwind at a high velocity when they detect an odor.